Lesson 1.5, Part 2, Inverse Functions with a focus on graphs. So in this lesson, we're still going to be doing the same thing, how to work with inverse functions, not only algebraically, but also graphically and numerically. Now, let's establish a technique for finding inverse functions graphically. We already know we can do it algebraically by switching the x and y values and then resolving for y, but how do we do it graphically? Well, let's start with two functions that we already know to be inverses, the x cubed function versus the cube root function. Now here we need to pull some information from Algebra 2. We need to make sure that we still recall what the x cubed graph looks like. That's that kind of S-looking curve where it goes down to the left and up to the right, intersecting at the origin 0, 0. And then the cube root function looks like this. Pretty much the same shaped curve, but going in a different orientation. Now look what happens when I take the two functions, the cube root and the cube, and put them right on top of each other. It's almost as if they're mirror images of each other, but not mirror images left to right, not mirror images top to bottom. They're actually mirror images across this line right here, and that line right there is actually the line y equals x, because that's what inverses are. It's where you replace x with y and y with x, so that this coordinate right here on one version of the function corresponds to this point right here where it's the same coordinate, just reversed, where x equals y and y equals x. So if I give you a function and ask you to find the inverse of that function, all we have to do is identify the coordinates, coordinate by coordinate on the original function, reverse them, and replot them to find the inverse function. And that's what we're going to do here, but before we get to that, a little bit more background information. We always want to be careful with what we call a function and what we don't call a function. Remember that a function is defined as each input having only a single output. You can have multiple inputs sharing an output, but you can't have an input that has multiple outputs. If I plug in x equals 1 and I get out y equals 3, then every time I plug in x equals 1, I only get y equals 3. I can't plug in x equals 1 and get both 3 and 5. The word function has to mean something. Now, every function has an inverse. If you can put something in and get something out, you should be able to reverse that operation and work back to the original input. Every function has an inverse, but not every inverse is a function. If I plug in 1 and I get out 3, that doesn't mean if I plug in 3 into the inverse that 1 is going to be the only output. Because remember, there's that possibility, maybe I plug in 1 or I plug in 5 and I get out 3 on the original function, which is perfectly fine. But then now we're pairing two inputs with that one output. The inverse function would now have a single input with multiple outputs. So just because I reverse a function doesn't mean that reverse is also still a function. A very well-known example of this would be the quadratic function, the basic parent quadratic function whose graph looks like this. Now, this is a function, not only because I know that x squared is a function, but because it passes the vertical line test. The graph of y equals x squared passes the vertical line test. It's a function. Now, using that mirror image technique, if I were to draw the mirror image of this graph across the line y equals x, I would end up with this graph right here. Notice if I draw the mirror just like this on top of the inverse graph, notice I get a full mirror image. But notice this graph no longer passes the vertical line test, which means this graph is no longer a function. The reason for that, y equals x squared being my original, if I look for the inverse, I would have x equals y squared. To get y by itself, I would square root both sides. But when I square root both sides, remember, anytime I square root something, I'm supposed to include a positive negative. So the function that I've graphed here, which is indeed the inverse, is y equals both plus and minus the square root of x. Now typically though, which I actually already did this in the previous lesson, and I failed to go through this whole process because I knew it was going to be coming back up later. Typically though, when I draw the inverse of x squared, I don't put the plus or minus here. I just go straight to square root. Now if I only include one option, then this is now indeed an inverse function. Because if I look at the graph of the square root function, notice I'm only including the positive. I didn't write plus or minus. I'm only including the positive, thus I didn't put any symbol at all. So that means I can basically ignore the bottom half of this graph, the negative half of this graph, and get this. This is the square root function that we've all grown to know and love from Algebra 2, versus this is the parent function that square root graph came from. By taking the inverse of the parabola, instead of the parabola opening up, the parabola now opens to the right. But in order to force that inverse into being a function, we only look at the top half. But the overall point that I'm making here is just because I draw the inverse of a function, that inverse isn't necessarily going to be a function on its own. Now the cool thing is we don't actually have to draw the inverse to know whether the inverse is going to be a function. The vertical line test tells me whether the graph in front of me is a function. Well, there's also something called the horizontal line test. If I apply the horizontal line test to the original graph, that will tell me not whether what's in front of me is a function, but whether the inverse of what's in front of me is a function. Vertical line test tells me whether this is a function. Horizontal line test tells me whether the inverse of this is a function. Consider this graph right here. If I apply the vertical line test, it's going to pass. That tells me the graph right here is indeed a function. Well, just like I can apply the vertical line test, I can also apply the horizontal line test. If I try to pass that horizontal line across the graph, following the same technique as the vertical line test, this one will pass the horizontal line test, meaning that the inverse of this graph, without actually drawing the inverse of this graph will also be a function. Now, if I go through the process of actually drawing the inverse, here's what the inverse will end up looking like. And notice the inverse passes the vertical line test. So if the inverse passes the vertical line test, then that means the original would have passed the horizontal line test, because keep in mind, the relationship between an inverse and an original function is switching the x with the y. Switching the x with the y is the same thing as saying switching vertical with horizontal. So the vertical line test tells me whether this is a function. The horizontal line test tells me whether the inverse of this is a function. Now, before we move on, just a bit of vocabulary. If a graph passes both the vertical and horizontal line tests, we describe that graph or that function as one-to-one. So if you see that phrase one-to-one, I'm simply telling you that the function passes both the horizontal and vertical line test. In other words, both the function and its inverse are functions. Here's another example. Notice this one. If I apply the vertical line test, it passes. This is a function. But if I try the horizontal line test, here is where we have a problem. Here's me drawing a horizontal line. Notice that we have more than one intersection. Therefore, this one fails the horizontal line test, and without even drawing the inverse, I already know that the inverse is not a function, and thus this graph is not one-to-one. And just to reassure myself, here is the graph of the inverse. Notice that the inverse would have failed the vertical line test, thereby proving that the inverse is not a function. So let's put all that together and actually answer some questions. So here is a graph. I want you to do two things. One, I want you to draw the inverse of this graph. And two, I want you to tell me whether that inverse is a function. So let's ignore the second half of the question. Let's just focus on the first half of the question. Let's draw the inverse. Now, remember, to draw the inverse, it's just a matter of reversing coordinates. So what I like to do is, off to the side, I'm going to go ahead and list out the coordinates that I see. Now, of course, there's technically an infinite set of coordinates here. Anywhere I pick a point, for instance, I could pick this point right here and identify that coordinate, but it's just not an easy coordinate to identify. I'm going to stick with the ones that are easy to identify. So I'm going to identify each one of these coordinates. I always read from left to right, so I'll start with this one at the bottom, which would be the furthest left. That's at -4, -7. Then -3, -4, and so on and so forth until I have all the coordinates, the easy coordinates that I can find on the graph. That's the original function. The inverse would be the exact same numbers, but in the reverse order. Just switch the x's and y's. Once I've done that, I can go ahead and start re-plotting my coordinates. -7, -4 is right here. -4, -3, -1, -2, 2, -1, 5, 0. Again, I could find as many coordinates as I want or as few as I want. I didn't necessarily need all 5 of these coordinates. I do see a line here, and when I'm drawing a line, I only need 2 points to draw a line, but the more, the safer you're going to be. So once I've plotted all the points, connect the dots, There we go. There is my inverse graph. This is my original, and this is my inverse. Now the second half of the question, is the inverse also a function? We actually could have answered that question first. Remember, I could apply the horizontal line test to the original graph to answer the question, is the inverse a function? So applying the horizontal line test to the original function would have told me, yes, the inverse is a function, or applying the vertical line test to the inverse directly would have told me that the inverse is a function. So either one of those answers would have answered the question. So I could say original passes the horizontal line test, or I could say inverse passes the vertical line test. Either one answers the question there. All right, here's another graph. Why don't you pause here, hit play when you're ready. All right, we're going to go point by point. So here's me identifying a handful of coordinates from the parabola, reversing the order of each of those coordinates, and replotting them. When I replot them, I remember that the inverse graph should be exactly the same shape as the original graph, just in a different orientation. So I'm going to draw a parabola, but instead of it opening up, it's now opening to the right. Now, is the inverse also a function? No, it's not. I could have answered that two different ways. I could say that the original function failed the horizontal line test, or I could say that the current function, the inverse graph, fails the vertical line test. Either one would be an acceptable way of answering that question. Here's another example. Pause here, play when you're ready. All right, this time, just for kicks, if I start with the second half of the question, is the inverse going to be a function? Absolutely, the inverse is going to be a function because I can see that this one is going to pass the horizontal line test. So I can answer that question first or answer it second. It doesn't matter what order I answer that question. Now, to draw the inverse, we'll do just like we did before. Let's list out some coordinates. There we go. Flip-flop them. There we go. Replot them. There we go. And then connect the dots. There we go. Always keep in mind, once you're done, you should be able to, take a step back and look at your answer. If your answer is not a mirror image across the line y equals x, if you can't draw the line y equals x to separate the graph into a perfect mirror image, then you know you've got a mistake. Also notice that the only place that the graphs would ever intersect is right on top of that line y equals x. So if you have intersections that are not on top of the line y equals x, you know you've made a mistake. If it doesn't appear to be a mirror image, you know you've made a mistake. Go back and fix it. Step back and look at your answer before you move on to the next question. Mine looks good, so I'm going to move on. And again, as I said before, the original graph passes the horizontal line test. The inverse graph passes the vertical line test. All right, last one. Pause here, play when you're ready. All right, doesn't matter how ugly the graph looks. If you follow the same process as before, we'll get the same answers. So let's go through and identify the coordinates that I see. I see all of those coordinates. Let's flip-flop them and replot them. Now, this time when we connect the dots, you always want to be super careful. When you're connecting straight lines are easy to connect. It's the curves that sometimes mess us up. So especially this part in right here, we want to make sure that on our inverse graph it curves right. Notice that it's going to be between this dot, and this dot right here, but we want to make sure that the curving is right. So if you don't have enough coordinates, feel free to grab some more. For instance, I can grab this point right here, which would be, let's just estimate that, that's about 0.6, 3. So I could put a corresponding point at 3, 0.6, so that when I get to graphing that part of the curve, I know it's not going to curve this way, it's going to curve this way. And then I could do more points. For instance, this right here, this would be 2.6. Well, that means I'm going to have something at 0.62. So I know that when it curves, it's going to curve something like that. You can get as many points as you need to make sure that the graph is curving correctly. So then when I connect the dots, look at that. There is my perfect inverse, and I can kind of imagine splitting this into two equal halves, right down the middle, across the line y equals x, where you're going to have a perfect mirror image. And as before, the original graph, remember that's the blue one, the original graph did not pass the horizontal line test, so I know that the inverse function was not going to pass the vertical line test, and thus is not a function.